I can.
Place. Okay, now that my mic is working, so we're back again. Welcome to our second part of our LIGO talk. I'm here with Riccardo DeSalvo and Tugdual LeBohec. Um, we're going to be talking about some extra stuff with LIGO today. Riccardo is a LIGO scientist. He's been working on LIGO for 30 years, almost 30 years. Tugdual, he's a physics professor at the University of Utah. He's been working with LIGO for about a year, and I don't work with LIGO, but I'm talking to them about it so you can hear stuff too. But I work at the Physics and Astronomy department with Tugdual at the U of U, and so we're here to expose you to the world of LIGO. Last time we talked a little bit about what gravitational waves are, a little bit of how LIGO works, what we plan to see with them, things like that. But today we're going to talk about some specific work that Tugdual and Riccardo are doing currently with LIGO to try to help enhance it so they can potentially see some better things with it. So we have a list of questions we'll talk about, and this one's going to be kind of focusing a little bit more on the engineering aspect of LIGO and a little bit of the physics that's involved with the engineering. Just to give you an idea that if anybody out there likes engineering and they like gravitational wave astronomy, but they don't want to actually do like the analysis of the gravitational waves, they want to do some actual physical engineering work, this kind of stuff is available for new and upcoming people to focus on when they're going through school. So maybe the next Riccardo that's coming through school right now can help build an even more awesome LIGO type detector out there. So
if you get another Ricardo coming, I'll be happy to be the mentor.
That would be great.
That would be challenging.
So yeah, we're going to talk about some of the engineering today. I think Tugdual is going to do a fair amount of it initially. Riccardo's going to hang back a little bit more today than he was last time. But he'll still be there to, fill in where we may be missing otherwise. So, so to start this off, we got to talk a little bit about the physics of materials. Why these kind of people are having to do this kind of stuff. I got to turn up my mic, apparently. Let me know if that is better, Tom. So, sounds better? Worse? Oh, yeah, I have to turn my mic up. So, we got to talk a little bit about the physics of why they have to do this kind of stuff in order to, find the gravitational waves. There's a bunch of physics that lies in the background of all of this engineering, and they have to go through and figure out, what these problems are, how to fix this stuff. That way, you can actually hear or see the signal itself. So, Tugdual, are you ready to take the first question?
Yes.
All right. So,
Ricardo is here to rescue me if I get in trouble.
All right, so our first question is going to be, what is the problem that physics has given you for the mirrors that you're currently working on?
Yeah, so let me bring a slide like that. You see that? Do you see that? You can? Or you can?
Okay.
So yeah, last time we talked a little bit about.
You may want to go on presentation mode.
like that.
Yes.
Okay. So last time we talked a little about how LIGO works, and so just maybe it's worth reminding everyone of that to get started with this. So here you have a laser that shines into a beam splitter. So part of the light goes into this arm of the interferometer, and part of the light goes into this other arm. And those two pieces of glass here, they are separated by 4 kilometers. And the goal of the game is to measure a relative change between the distance of these two between these two pieces of glass and the distance between these two pieces of glass as
Hey,
a function of
Tugdual,
time and the amount. Sorry.
one second, real quick. Your mouse isn't really showing up, so if you could
Whoa. I don't know.
say the portions that you're talking about. I know you're talking about like the where it says
So
light storage arm.
there are these pieces of glass that are labeled test mass, and there are two of them on each arm of the interferometer, and they are separated. Each pair is separated by 4 kilometers, and the goal is to measure a change in the distance between them by an amount of 10 to the minus 18 meters about. And this is done by making these mirrors highly reflective in such a way that the light goes back and forth something like 1 million times, in such a way that if one of the if the distance changes by 10 to the minus 18 meters, then as the light goes back and forth 1 million times, this 10 to the minus 18 meters of extra or shorter distance is multiplied by 1 million. And so,
1,000 times, 1 million times, it would not work.
oh, 1,000 times,
1,000 times. Because
1,000.
4 kilometers, the arm will become 4,000 kilometers. If you add a million times, the arm would be 4 million kilometers, and there would be trouble.
The reflectivity of the mirror is one part in the
Yeah.
loss is 1 part in 1 million, yeah?
And the part will be 1 part in a million. But the input test mass is 1 per 1,000. They are different. So the end test mass have 26 layers. The
Oh, right. Yes. It's limited by the first one, yes.
It's okay.
And so I got derailed here. Where was I going with this?
Light goes 1,000 times.
And then the light comes back here and is combined to form interferences. Uh, and so any displacement of the test mass comparable to 10 to the minus 18 that is not due to gravitational waves is going to affect the signal that is recorded by the entire system. And so displacements or changes that are not due to gravitational waves would be identified as noise. And on the graph that shows displacement noise as a function of frequency, you see a number of curves. And one curve that Riccardo talked about last time is the purple one that represents what you can do with the light that is actually circulating in the interferometer. And then in the region where the system is the most sensitive, that means where the black curve reaches the lowest, uh, you see that the first curve that is not the purple one that you encounter when going downward is the red one. And this red one is labeled coating Brownian. That corresponds to the fact that the mirrors, because they are at a finite temperature, they they have some vibration motion that is excited, which degrades the contrasts in the interference fringes that are measured by the interferometer. And so what we are working on with Riccardo is bringing this red curve down so that the overall sensitivity in this region of maximal sensitivity is maximized. So that's the game.
Before you go out, a small correction. Uh, 10 to minus 18 is the amplitude of a gravitational signal we expect. Of course, if a system would have noise 10 to minus 18 meter as well, you would not distinguish. And you can see that the curve of sensitivity goes below 10 to minus 19. That means that we have signal to noise of the order of, let's say, 10 or a little bit more here and there. And every little bit helps because the signal is weak and we need high sensitivity there. Yep.
Voilà.
So, Tugdual, is the coating? What are the properties of the coating that cause the noise? Is it the vibrations of the atoms in there? Is it the interactions with the light off of the surface? What is exactly that you're talking? What is exactly that you're having to do with that?
So maybe before getting into those specifics, so in 1916, Einstein came up with the idea of gravitational waves from his equations of the general relativity that describes gravitation. And but before that, he was quite famous in part because of his papers that he published in 1905. And there are three papers that were carrying a lot of impact. Two of them are more well known than the third one. The one of the very well known is the one on the photoelectric effect, which established the existence of the photon. The other paper is the paper that in which it describes what is known as spatial relativity. So the fact that, for example, time that we experience depends on the relative motion. And the third paper is a paper in which he demonstrates a relation between, so specifically, he was considering a particle that is dragged through a fluid. And so when you drag, if you drag a chair, for example, through water, you feel a force that is exerted by the water on the chair that you're dragging through the water. And he found a relation between this drag and random motion or diffusion motion that is experienced by any object in a fluid at a finite temperature. And so that's exactly what we are dealing with here. Of course, we're not dragging a chair in water, but we're just looking at a piece of glass that reflects light. And so that's something that is quite familiar. If you bang on a glass, so the crystal glass, it's going to ring, producing a sound, and the sound is going to decay because the energy that you have conveyed to the glass is dissipated by increasing the temperature of the material. So that means that there is a communication between the mechanical energy in the glass and the heat energy that is stored by the glass. And this communication can go both ways, right? So if energy from the vibration is dissipated into heat, you can have the reverse, which is heat exciting mechanical vibration. And so what we want to reduce is just that flow of energy between mechanical vibration and heat. And then to get to the specifics of LIGO, the mirrors are not the mirrors that we use in optical telescopes. For example, in optical telescopes, we have a piece of glass that constitutes the mirror that is coated by a layer of metal, and the metal reflects the light essentially because it contains electrons that are free to move. and under the influence of the electromagnetic wave of the radiation that is collected by the telescope, these electrons they move and they emit themselves a wave which collectively is emitted in the direction that corresponds to our usual experience of a reflection on a mirror. Such mirrors could not work in LIGO because the power that is delivered by the laser is way too high for that to be working. So instead, in LIGO, we are using dielectric mirrors that are represented in the schematic. Here you have even a picture that I just found before this started. But so you have a ray of light that arrives from the left side, and you see that part of this ray of light is reflected by the top layer, and that's dielectric. So it's like a glass, right? So the first darker layer corresponds to a higher refractive index, so a region of glass where the speed of light is reduced. The speed of light in materials is not the speed of light in vacuum; it is smaller than the speed of light in vacuum. And so there is a first ray of light that is reflected at the top of the mirror, and there is another part of the light that gets transmitted to the deeper layers. And you see when you get to the second darker blue layer, there is part of that light that is reflected. And you can set up the thickness of these layers in such a way that for the wavelength that we are using in LIGO, which is 1064 nanometers, so that's about twice the wavelength of the light that we have in the center of the visible spectrum. The ray of light that is reflected at the top and the ray of light that is reflected on the second higher index layer, they interfere constructively. And so that means that they will reinforce each other. And you can repeat this over a large number of layers. And the larger the number of layers, the higher the reflectivity that you will achieve. And so if you look at a piece of glass that is not coated in this way, and you were to tap it with something to make it vibrate, it will vibrate for a very long time, indicating that there is not much of an exchange of energy between the mechanical vibration of the glass and the heat of the glass. But if you apply this coating, suddenly this exchange of energy is much stronger. And so the vibration of if you were to tap the glass again once it has been coated, the glass will keep vibrating for a much shorter time, about 100 times shorter actually. So it seems that this exchange of energy is taking place in the layers of the coating. It seems that the mechanism through which this exchange of energy takes place are not very well identified, but Riccardo convinced me about 2 years ago that we should look in the idea according to which in the material of a higher refractive index, there might be small crystals that form, and at the surface of this crystal would be the sites where energy communication between heat energy and mechanical vibration takes place. So what we are trying to do is prevent the formation of these crystallites in these layers of high refractive index. The material of the lower refractive index does not crystallize, so that's why I did not indicate anything in this layer. And so it's not believed that there is much energy transfer taking place in those layers.
Is the crystallization that you're talking about, the formation of the crystallites, is that during the production of the mirrors itself, or is that caused by an interaction with the light and everything?
No, it's during the production of the mirrors. To achieve the best qualities of the mirrors that you want to have, it requires bringing the mirrors to some high temperatures. I would not give you numbers, a few hundred degrees. And when you heat up amorphous materials, at least some materials, they produce these crystallites. So it's an inconvenience that shows up in the course of the fabrication of the mirror.
So that's similar to like when you make a piece of glass, they do a thing called quenching, where you cool it down really quickly to slow down the formation of the crystallization, which that's what makes glass clear. And so that's kind of what they're dealing with on this also.
I don't know about that.
Yeah, same and different. Yes, similar but different.
So yeah, similar but different. So the reason why the mirrors have to be brought to a high temperature is to relax the materials in these layers, and also to bring in oxygen, because in the deposition process, these glasses, they are oxides, but in the deposition process you may not have all the oxygen that is deposited. So by bringing the glass to a high temperature, you may bring in oxygen that guarantees the transparency of the glass.
Yes.
Or the
So that
coating.
is the
I'm
first
talking
thing.
about the coating, not the substrate, right? The coating.
Yeah. The substrate is actually super pure fused silica, silicon oxide, and its quality factor it's above 1 billion, not million, 1,000 million. Then when we make the mirror, we deposit these coatings at 26, 19, depending on which mirror you're talking about, by evaporation. So we evaporate under vacuum. Now, when you evaporate even fused silica, its quality factor with the number of oscillation it does before it dissipates two-thirds of its energy into a thermal bath goes into maybe 100,000 or so, or a million. And the eye refraction index goes into several thousands. So let's say 5 to 6 to 10,000. And so you understand that the substrate, which is very thick, have a quality factor of a billion or more. That means it's talking with a thermal buff is less than one part in a billion. And the coating, the bad part, the N1, the heavy refraction index material, has a few parts one part in a few thousands. So you see that there is an enormous imbalance. And even if these coating are only 5 microns, 5 micron is 1/20th of a hair thick total, and deposited over 20 centimeter thick fused silica, which has a talking with a thermal buff more than a million times less. The coating is what generates the interchange of energy, most of the interchange of energy with the thermal buff, and therefore what is called the thermal noise. I hope I was reasonably clear.
Okay, so
So maybe your next question is maybe how do we intend to reduce the presence of these crystals?
right. So yeah, how are you working to solve the issue of these crystals?
And again, I'm the one talking, but that's an idea that comes from Riccardo. The idea is that so again, the thicker layers, they could be silica, which do not produce these crystals. And the thinner layers, they would be the higher refractive index. So silica has a refractive index of 1.5, and the material that is used in for the high index to the thinner layers is Tantala at the moment, I think, in LIGO. It has a refractive index of 2, right? So by combining these layers, you get this reflective effect that I was describing earlier, which is also when you look at sunglasses that reflects very bright colors, that's exactly how it's obtained as well.
It's the same thing that you see in soap bubbles.
And in soap bubbles as well. Yeah. And so to prevent the crystals, the small crystals to form in the processing of these layers with heat, Riccardo had the idea to segment each layer into nano-layers. So if you had, for example, the thinner layer being tantala, but tantala that is interrupted every, and I'm giving numbers at random, right? For example, you could imagine tantala that is interrupted by a thin layer of silica every 2 nanometers, then you could not form any crystals of more than 2 nanometers. So essentially, you would not form any crystals. And so that's exactly what we are trying to do. So we have colleagues that are creating samples, so small glass samples with coatings that are segmented in this way so as to prevent the formation of crystallites. And we do two things. We measure how the crystals end up appearing as a function of the thickness of the nanolayers, so as a function of the thickness of the material that can crystallize, that is interrupted by another material. So we try to identify these properties.
Yeah, the
So
coatings, the samples are made in Italy. So if one student is particularly interested and he wants to make a thesis on, he may get shipped over to Italy to make some work there and then bring the stuff back and measure and go back and forth. Yes, that's what I do. Typically in the summer, I try to go there because Pasadena is too hot.
No, it's a beautiful region as well.
Yes.
so I have a question that kind of is kind of jumping off the thing. So a lot of people they don't realize some of the benefits that like research like this has. Um, so when you're developing these kind of new methods of reflectivity and things like that, what is there a way that you could use this kind of thing in other industries that could potentially benefit from this kind of research?
Maybe Riccardo should take that question.
Yeah, there is a number of uses. For example, all the satellite of GPS and many satellites and many precision clocks that you have on Earth, they are called the atomic clocks, and they have atoms that are vapors in cavities. And these ones are also limited by the thermal noise of their own mirrors. This one have cavities that have finesse of hundreds of thousands, even million, not 1,000. And that is one case of a metrology definition of units, and that can be gained from that. So anything that needs a special precision timing. And then there are other uses which are possible and not there, but they're possible. Crystallites also scatter out light and generate energy loss. And so the mirrors that have less scattering may actually be used in directed energy weapons to defend yourself against incoming bombs. Don't believe directed energy weapons are Star Wars. They essentially can work only in vacuum because laser is diffused too much by air. But if you have an incoming rocket and you have a good directed energy weapons, you can probably make a hole into it, and that is useful because a bomb with a hole does not blow. So it's a defensive weapon. But anyways, this is another possible use that metrology in general give precision to better GPS and better clocks, better definition of units, and then to very high power lasers by reducing the losses inside the laser cavity.
All right, cool. That's that brings some interesting things to the table. Um, so should we move on to the next question, or do you have a few more things you want to talk about with this part?
No, I forgot what is the next question.
Next question was going to be, how is this going to impact the data that you hope to see from LIGO?
Ooh. Um, so okay, so I don't know to which extent people are familiar with the inverse square distance law, but when you have a source of any form of radiation that is represented by this blue dot S, the radiation is emitted in all directions. And so if you are at a distance r compared to being at a distance 2r, you see that the energy that is received per unit area is decreasing like the square of the distance. And since we have many amateur astronomers, I think, in the audience, this square law works also for the angular size of objects. So that's essentially the reason why the surface luminosity of galaxies do not depend much on their distance, because if you consider two identical galaxies with one twice as far as the other, we will receive from it 4 times less light per unit area, but it will also appear 4 times smaller in area on the sky, and so the luminosity per unit area is the same. And so the same goes for gravitational waves. The power that is received per unit area decrease like the square of the distance of the source. And so if we improve the sensitivity of gravitational wave detectors, we can see further out. Now, the difference maybe is that compared to what we do with optical telescopes, in the case of gravitational waves, we don't measure the energy that is deposited. In fact, there is no energy almost deposited by the gravitational wave. What we measure is really the amplitude of the wave, and the amplitude of the wave has to be squared to give the energy. So that means that if you um, improve the sensitivity by a factor 2, um, you can see out twice further instead of square root of 2, right? Further in the case of light. And so if we were able to improve the sensitivity of LIGO by a factor 2, you would be able to see at greater distances by a factor 2, which corresponds to increasing the volume of the universe that you can see by a factor 8, right, which is 2 to the third power. So that's a huge increase in the number of events that you can see per unit, that you could detect per unit time. So in the case of what we are doing, I don't know how much of an increase, but if you increase by just 10%, it's already a huge gain in the volume of the universe that you can survey with the sensitivity of these gravitational wave detectors. So that's just increasing the number of events per unit time, and improving how well you can model and understand the events that are not too difficult to detect, so not too far away.
Yeah, it may be worth noticing, well, because gravitational waves are sensitive to the amplitude of a field and not to the power, as Tugdual said, is every improvement of 10%, 20% has to be cubed to as a detection rate. And this one is equivalent to what happened in radio telescopes, because in radio telescope you also measure the field. And it's not the same, for example, if you look at the gravitation, no, the cosmic microwave background, because in those one they use calorimeters, and calorimeters just use the energy. So if you pick up the the electromagnetic field on a radio receiver, you get the field, and your depth perception goes down like 1/r. If you do it with a calorimeter in a cryogenic detector, that one goes down like 1/r square. So that is fine. So that's why we are going so deep into the universe. We just started detecting, and we are talking already in the next generation to get closer to the edge of the visible universe. Now, increasing sensitivity as not going deeper in the universe is not the only thing that is important to us. It's extremely important. I told you last time that a gravitational wave detector is actually a transducer of the motion of the orbit. So you have a certain orbit, and gravitational wave detector will transduce that orbit into an electrical field that has the shape of that orbit. Now, if you do that, the game is to go and see how much that decaying orbit or accelerating orbit is not decaying, it's decaying in diameter but accelerating in frequency. How much does that follow the general relativity, and does it violate general relativity? Now, in black holes, black holes are generated by general relativity. We have no expectation that there will be a variation from the orbit required by gravitational wave emission due to general relativity. If we find it, of course, we are checking. If we find it, we'll be very excited. That means that Einstein was wrong. However, if the in-spiral is due to neutron stars, towards the end, the neutron stars will go from spherical. A neutron star is spherical within a few microns. It's 10-kilometer diameter, spherical within a few microns, and I can tell you about that at some point. But at the end, there is so much tidal force, like the one of the moon to Earth, that they become oblate, and then eventually some part is shredded out and thrown out, and the rest falls in. And this one will cause the orbit to violate from the pure prediction of the general relativity. And so that one will measure how stiff is the neutron star and how easily or difficult or whatever it is to shred and emit neutronic matter out of it. And that one is something of enormous interest to understand and probe out how a neutron star is built out. And that one actually, maybe we'll get to talk about that, will also require a lot of optical astronomy to support. But I don't know if we have time to get to that. But in any case.
But in more general terms, increasing the sensitivity of any instrument allows to detect fainter signals, and also at the same time, it increases how constraining is what you detect when you compare what you detect to the models that you use to describe what you detect.
Yes.
And so if you have a simple picture of the source that you have been observing, by improving the sensitivity of your detector, you're likely to break your simple picture, which you will have to make more complicated, so as to develop a more specific understanding of the object that is responsible for the emission that you have detected.
Which has happened already a few times in the past. You may recall how the orbit of Mercury, measured with higher and higher and higher precision, eventually did not agree with Newton anymore. And then that disagreement is what brought Einstein and others to think about a different wave. It was first special and eventually general relativity. So
That's something I like to tell my students in class. In physics, there is no truth.
absolutely,
You can only be wrong.
yeah. Anybody that tells you it's incontrovertible is not a scientist, a charlatan.
Okay. Let's see. I think that actually leads us into the next question fairly well with what Riccardo was talking about, and so like this kind of actually we kind of been talking about it, but how much farther will this allow you to probe into gravitational waves? We kind of talked about that just a little bit just now. In being able to see the amplitude and twice as far into the universe, if you have that kind of stuff. Does it allow for any other things? Maybe with something. I think you mentioned doing. Oh, what was it? Doing work with an optical components and other. Like multi-wavelength astronomy and stuff like that. How well does this kind of thing, when you increase that signal, how well does that lead into being able to probe with other sources of detectors?
Yeah. Let me see how do I present now share the screen here. I hope that's it. I'm not sure on this thing. Present your entire screen. That's okay. Good. So select window or screen, send optical mix or entire screen. Okay, good. Allow. So you should be seeing my screen at this point, don't you? Good. And now you have to allow me to, yes, let's do something. I have to look for, because as I say, as usual, I have to find what I want to show you. It's the thing. The screen is updating here. So good. Let me see here. And you got me a little bit by surprise. And yes, I think this is it. There. So, if you look at this, is last time I think I got you to listen to a short two black holes falling. Remember the one radiating free detectors, free solar masses in 0.2 seconds. But if you look into here, I don't know if you see my pointer, there is a line building. And if you listen carefully, you hear a hiss. Did you get it? That whoop at the very end? Let me do it again. Very end. You got it? I hope that people over there can hear it, but I'll get you to listen to this well. So here I have three interferometers. Okay. So this one is Hanford, this is Livingston, this is Virgo. And what you see here along, do you see my pointer? This line here and this line here is the signal detected in Livingston that was very strong, in Hanford was weak, and in Virgo it was substantially weaker. Now I'll get you to listen to this in yeah, it is already going. It's about 10 hertz here. These one were previous events. And this frequency is going up. It will take some time, but at the end you will hear it. Is now we cancel the noise of interferometer, the hiss, which is also white noise. Can you hear the hum on the back? Oh boy, you don't hear anything. Let's see. Let's go toward the end to make certain that you can hear something. It's coming there. Yes. So did you hear this? Okay, if I go back where it was already there, only it is barely audible because I mean, a whale would have no problem listening to this because it's 10 hertz, and then it becomes 20, and then becomes 30, and then becomes all the way to a few kilohertz. Okay, so at this point, probably it is something like 30 hertz. Okay, and these are the orbits. So the line that you can see, that you cannot see, are the orbits of these two stars, the last few thousand orbits in the last 30 seconds before the neutron stars will fall into each other. Okay, and I'll let you listen. So now you got this. This one is the signal transduced of the orbit. So all of this sinusoid that you can see is the projection of the orbits, well, twice the orbit, that of these two neutron stars were falling into each other. Okay, and now you say, and that is what we have seen. Now, there was something interesting why Virgo did not see it. And that one, to make it short, I will not bother you, is because it was on the blind zone of Virgo here. And so by knowing that it has to be on this line here and nowhere else, we pointed to this point here, and we told the optical astronomer, hey, look over there. Not only this, but over there are zillions of galaxies. But because gravitational waves from the shape of the orbit, we could immediately say how strong the signal should have been, and we measure how strong we got it. We could say it should be at that distance there. So we gave a position in X, Y, and Z in distance. And when we gave that to the astronomers, there were only some 80 galaxies that could have housed this. So the astronomers started looking in there. So this one is the area that we defined, but not only this area, we also said it should be right in that bullseye at a certain distance. And there were something like 80 galaxies. And all the astronomers like you started looking into that like crazy, one after another, to see if I could see any flash. And you see here, this one is a photo 20 days and a half before. It was taken by accident in that area at low resolution because nobody was looking for anything there. And this one is the light 10 hours after. It took 10 hours to screen one place after another. So astronomer could say, wow, there is a flash of light there. And and I'll come back to the importance of that in a moment. But also, what happened is that the Fermi Gamma Ray Telescope, which is something that it so happened that me and Tugdual's mentor worked on for a while together, but then we dropped out because we were doing something else, said, oh, there is a gamma ray burst coming from this area here. So Virgo and LIGO said it should be about here. The astronomer told us, oh, it's right in that corner. It's this guy here. And the Integral, which is another satellite, told us it's around there. So we got a multiple messenger signal here. The only missing is neutrinos, which of course are too weak to be detected from an event like this. Maybe different for supernovas, but in this case, you don't see neutrinos enough. So we got this, and so let me go and see the interchange or synergy between different astronomy, branches of astronomy. So this is our signal. It went like whoop, and it dropped here. Fermi and Integral got a signal 2 seconds later. And the event was 100 million light years ago. So 2 seconds over 100 million light years means that we measure the speed of light and the speed of gravitational waves to be equal within 1 part to 10 to minus 16, and actually the light came back. So you'd say, oh, if it goes slower, came after, you could say, oh boy, the photon has a mass and the graviton does not, because the mass is a slowed down thing, which would be the wrong conclusion, because the rest come from the optical astronomer that pointed there, and they just looked at the shape. So what is happening when you have two neutron stars? They will orbit into each other and they eject garbage, neutronic matter outside, while the core, which you don't see inside, this one, this part, this size here is something like 20 kilometers, but then the core of this will collapse into a black hole of 2 or 3 kilometers only, just bloop, and disappear there. And now the fact is, what's happening this and where the gamma ray comes from. So the gamma ray comes from this ejected stuff that has to climb out the gravitational well of the black hole, which is inside there. It's not in the black hole, it's outside. So this ejected matter, ejected at close to the speed of light, get ejected out. They are coming out at each nucleon has maybe 10 mega electron volt coming out, but as they come out and they climb out this potential well, they got slowed down and cooled, and then they start sticking together. And well, this is another view on how stuff are emitted. And between 1% and 10% of a neutron star mass is ejected. So these ones are free solar masses, so even 0.1% is a lot, okay? And it has to do because you have to conserve the angular momentum, and you cannot store all of it inside there. This one is an accretion disk. And so what comes out, now, when it gets out, it starts emitting gamma rays, and that's because that's what it takes 2 seconds to decay and emit gamma rays. Now, where are the optical astronomy? Optical astronomer looked at this, and this one is a light curve, and you see these are days passing, 3.4, 3.5 days. Let me go from the beginning, because where is it? Yep. Up. Nope. Where are we? No, this. Nah, there. You see, this is 1.5 days, and then it's becoming, so this one starts in the blue here, and then it's going towards the red, and this curve is a light emission curve that is emitted. Look how beautiful you, astronomer, have done, okay? Now, these one are holes of in atmosphere, but this turns out it is extremely important to figure out what the heck was happening there, together with elasticity that we measured before. So this one is essentially all in there. Now, the emission here in the infrared means something which is quite important, and means that that one is fluorescence from lanthanides, and lanthanides are essentially the heavy metals, but nobody knew how you could generate. And how important is having measured that color? You see, the black one is the color curve that you have seen before in the animation. So the first day when we started measuring, it was in the blue, and it started going towards the red, and then more toward the reds, and that's where the fluorescence of the heavy metals is. And I remind you that heavy metals cannot be generated in neutron stars. So where does the uranium come from? Where is the gold factory of the universe? We found it here. Now, these one are simulations that were done before, okay? And they differ from the amount of, we say protons here, but inside the neutron star, it's probably a mix of different quarks that could not just be the up and down quarks. You may have some strange, you may have some other charm quark or whatever in there. And so when you free them up, because you eject this matter and they are not stabilized anymore by gravity, they start decaying by hell. And I'll get you in a moment. So by this curve here that you optical astronomers have measured, together with the elasticity that we get from the deviation from the orbit shapes that you expect from general relativity, we can actually say how in the hell is built a neutron star inside, okay? So this one, of course, were things made blind because nobody had these measurements. But now that we have this measurement here, we can, that these people here can do better there. And the next thing that I'm showing to you is this. So let me stop it here. So, stop. So beginning, and I go back a little bit, here is the ejected matter. We'll have a certain amount of, so down here is all neutrons. Over here it will be all protons. And these empty squares are the known stable isotopes. And over here someplace is uranium. So when you eject matter, you have a little bit of neutrons, mostly neutrons, and some protons, and that one comes from the curve that you astronomer has measured how much, okay? And then as time goes, and they cool down because they came out of that black hole well, and that one took a lot of energy out. Now, these neutronic matter, which were atomic weight of 40, 50, they are cold enough that they can stick together. So you can take two of from here and move them over, and you glue them up, okay? And so you see, as time goes, they glue together. These one are a fraction of seconds, and they are moving up there. And now, after a while, all of these neutrons start decaying after a couple of seconds into protons by emitting gamma rays. And these are the gamma rays that we have done. So they populate all of this area over here. And then all of these are transuranic. And then later on, they start decaying down into, and then they populate all of this area here. So the bottom here was all populated by the supernova and the star forging hydrogen all the way into iron. But stars cannot go much beyond iron. All of these, the gold factory and uranium factory and lead factory and tungsten factories of the universe actually were, what's the name? Neutron star merger. And we can confirm this. This was a simulation made before. I didn't put, yes, 2015, before gravitational wave discovery. That was the first one to 2017, and this neutron star was even later. But now we can constrain these models because of you guys. Okay? So I hope this one was of interest to you. Let me get out of this. Sharing, stop presenting. Good. I'm back.
So I just had a question. So we have evidence of gold on planet Earth. So that means at some point in time there was a there was a neutron star merger whose stuff came in contact with our protoplanetary nebula and kind of seeded our solar system with that leftover neutron star stuff.
Yes.
So now that if you have like gold on your ring or somewhere else, you can basically say that, oh, some of this probably came from neutron stars colliding and turning into black holes.
Well, in my fingers, no, but in my mouth, yes. Yes. So there was also evidence, also from astronomers, that something like this was happening even before. Because you have to think that the majority of stars in the galaxy are dead stars, that many of those went in supernovas. And in fact, if you look at all galaxies, from the spectrum of everything all the way to iron, they are all very similar, because the number of supernovas, the fraction of supernovas that produce metals inside them, is more or less constant in all of those. And then if you go and look at the color of the fluorescence of the heavy metals, which is in the infrared, that was only visible later on, because beginning the astronomy was only eyeballing into a telescope. It's only with CCDs and other stuff that measured in the infrared. Then they could see that some galaxies are more luminous than others in the infrared, compared with what they are in the visible. And that means that these lanthanides must be generated by very rare events. So a galaxy typically may have a few inspirals in its lifetime of neutron stars. So if you say you have 6 inspirals, the fluctuation from galaxy is 6 divided square root of 6. And so the fluctuation of events like this is large. Then the space winds mix all of these gases inside the galaxies quite uniformly, at least since from far away. There are areas in our galaxy which is more metallic and less. That depends on where the gas come, if it is extragalactic raining in, if it is mixed inside. But seen from far away, a galaxy, as it was pointed out by Tugdual there at one point, then you just look at the integrated color and you see that some are more red than the others compared with the blue that they emit. And that was telling us that these events were rare. And in fact, supernovas are often, and then a neutron star in spiral, you have to have 2 supernovas that somehow are close together enough that then they can inspiral due to emission of gravitational waves.
So what you're saying is that it takes a long time to do all this.
I didn't get it.
It takes a very long time for all of this to come together to form a planet like we have.
You can make a planet without heavy metals. By the way, there is a reason why heavy metals are called rare metals, because they are rare. It's only small amount that cause them. They're rare event.
At the same time, the life cycle of stars that produce
There's echo. Somebody's producing echo here.
Yeah.
Okay, go ahead.
At the same time, the life cycle of the stars that produce these objects is quite short as well.
Yeah, the lifetime that the stars that produce a supernova is of the order of 10 million years. And the lifetime of bringing together two neutron stars, supposing that they are close to each other to start with, because that is already there, it's billions of years. So you have a factor of 100 only in lifetime. But in addition to that, you have the fact that you have to have two neutron stars that by accident are orbiting each other. And if you think about it, most stars start double. But when they go supernova, this one was 20 solar masses, and then all of a sudden it ejects matter, and then it remains only 1.5. So its power to retain the other one without separate from the other is diminished by a very large factor, and a factor of 10 at least. So most of the cases, the supernovas separate the neutron star from the companion 10 or 20 solar mass companion that goes elsewhere. They only stay together if by chance the supernova gives out a kick, a natal kick that is in the right direction and keeps it in orbit, or actually makes it in a closer orbit.
All right, so it looks like we're about an hour in. So do you guys have anything else to add? And do we have any questions from anybody watching right now that you guys want to ask really quick before we end? Have anything to add, Tugdual or Riccardo?
I mean, we answered your questions. There is plenty to tell you if you want, but yeah.
Okay, great. So
I think chances are that Yue will come back. I don't know if he will come back next week from China, but he can tell something about the gravitational wave background and a few other strange things, axion stars or exotica that we may be looking for with gravitational waves. But anyways,
yeah.
Maybe one thing I can add is so clearly the detection of gravitational waves is exploiting interference of light. When we study these crystals that form in the layers of the coating of the mirrors in LIGO, we use the interference of X-rays. When we measure the vibration of samples of glass are filtered in different ways, use the interference of light. We are doing everything, interferences. And if I have a terrible echo here, which is not interfering constructively. And there is one book that I can recommend to the people listening. Is a book by Feynman that he wrote for a friend of his who wanted to understand more about quantum mechanics, which is wave mechanics. And that's a book that is entitled QED, the Strange Theory, maybe. But QED is the main title by Feynman, and it's a very entertaining and educative read that I recommend to everyone. I like reading that book myself.
All right, great. It doesn't look like we have any questions, but yeah, we hope our next presenter is back from China maybe next week or the week after, and we'll continue to talk about the analysis a little bit of gravitational waves. So what happens after Riccardo and Tugdual like send out all of the data into the world for other people to analyze? Like, how does it get past that point? So hopefully we'll talk about that after, or maybe next week or the week after. If there's anybody with questions, feel free to post them on our Facebook We also have an email. It's observatory@physics.utah.edu. That if you send us a question on there, I can forward that to whoever's willing to answer some questions. So, thank you guys again for helping us discover a little bit more about LIGO and learn about gravitational waves even more. So I guess have a good night. See you guys later.
Bye. Thank you.